All right. So it is 3:30, so I guess we can go ahead and get started. Yeah, how's everyone doing? Hopefully good. Oh, thank you. Yeah, great. So yeah, again, takes me like a second to code switch from 207 brain to 437 brain. But yeah, just start off with a little bit of housekeeping before we begin. Um, So I haven't posted information about first,
Oh, it's okay.
but I will be doing that on Friday. But again, just as a reminder, our homework assignments tend to be comprised of one component that will involve coding in a Jupyter notebook that I will give you. So I would say, um, if you've never coded in Python before, I would emphasize making sure that you have some sort of software that allows for you to edit Jupyter Notebook files is a good first step in, preparing for that first homework assignment. And yeah, so the instructions on the website give you one such way of going about doing that. So you can, download Miniconda. On the other hand, I think other people sometimes use like VS Code to edit their Jupyter notebook. So if you prefer that, that's totally fine as well. So if you're having issues getting any of that set up, Jordan and I do have office hours starting this week. So I guess I'll have my office hours this Friday. And yeah, I think that's basically it. I wanted to finish up with a few additional parts of the course introduction PDF. But basically, right after that, we're going to get into our first unit, which will be an introduction to the overall task of cluster analysis. So we're going to talk about one of the most common clustering algorithms that exist, which maybe you've guessed it, is k-means clustering. So we're going to dive a little bit deeper into the mathematical optimization roots of k-means clustering, and we'll talk about how to go about coding that in Python. Okay, but yeah, any questions before we get started? Okay. So a couple things I wanted to wrap up with where, again, I'm basically just outlining the course goals of what we hope to accomplish um, by the end of the course. So again, you know, the final product, if you will, for this course is basically enabling you to conduct a full unsupervised learning analysis from the beginning of the data science pipeline to the end of the data science pipeline. So we talked about some of the questions that specifically you would need to think about when it comes to actually, completing that full unsupervised learning analysis. So for instance, if you're conducting a cluster analysis, you want to think about, well, should we even apply a clustering algorithm to this data set in the first place? Or in other words, is your data set clusterable? And then, if you do decide that the data set is clusterable, you next want to think about, based on a variety of different pieces of information, what is the most appropriate clustering algorithm to use on that data set? Once you've picked a clustering algorithm, you want to think about what are the appropriate parameters to look for to use in that algorithm. Um, in addition, once you have clustered your data set, for instance, you want to think about, well, how would you go about evaluating how good your clustering algorithm result is? So again, unsupervised learning analyses are a lot more complicated when it comes to evaluating how well we did. And part of the reason why is because, again, in an unsupervised learning analysis, we're never actually given the answer key or the set of response variable values like we are in a supervised learning analysis. So therefore, we need to put a lot more thought into not just how we design the algorithm that clusters the data in the first place, but then how do we evaluate the results? How do we know that the algorithm was performing well? And so again, based on the type of data set that you're using, that can also dictate how well your evaluation metric might, do when it comes to evaluating the result. In addition, in this full unsupervised learning analysis, you should be able to, not just cluster your data set, but extract useful insights from the results of your cluster analysis. So you need to be thinking about you know, how might a manager or how might a client find the results of your cluster analysis useful? How do they how would they use that to help, maximize profit, for instance, something like that. Um, Now, in addition, like I mentioned, I don't like to teach any of my classes in like a petri dish kind of fashion. I very much like to place the algorithms that we're introducing within the full scope of the data science pipeline. So that means, thinking about how might data cleaning decisions that you make, for instance, prior to running your clustering algorithm, how might that alter your results? And furthermore, how might that impact your research goal that you are pursuing, with the overall analysis? And furthermore, we want to think about, well, after we've clustered the data, which again, clustering is a descriptive analytics technique. We're using it to describe the data. So once we've described the data set, how do we use our insights, for instance, to make effective predictions or make good business decisions, so a good prescription? So we're going to be thinking about all of these elements of the data science pipeline when we introduce these algorithms, as well as when we write up our final reports. Okay. All right, so questions on that? Okay. And then one final thing that I wanted to discuss about, also what we're going to be doing in this class is, in addition to, writing up a full unsupervised learning analysis, we also want to develop a deep knowledge base and intuition for how and why each of these unsupervised learning algorithms works. So in general, you should know, how does the algorithm work and what is the output of the algorithm? So, whenever we introduce a new algorithm, most likely you will have to write out a iteration of that algorithm by hand in the homework assignments. And now this goes for the actual algorithms themselves, as well as the evaluation metrics that we use to evaluate the results of the algorithms. Now we're going to be looking at a lot of two-dimensional data sets, which we're going to see are, not the most useful applications for applying a clustering algorithm to, because basically with a 2D data set, we can see that data with our eyes. So we don't really need to use a clustering algorithm on it most of the time. But we're going to be using a lot of two-dimensional data sets so we can develop a deep intuition for, basically how a given algorithm will work on different types of data sets or different types of clusters. Yeah, and so basically we're going to learn how to code these, each of these algorithms that we're going to learn in Python. Yeah, and that's basically what we have to do in the class. So any questions on that? No? Okay. I'm noticing that my pen does not work on the left-hand side of my screen, which is really annoying me. Sorry about that. Okay, so if there's no other questions, we'll move on to the first unit. So, which is going to provide us with an introduction to clustering. So again, like I mentioned, what I'd like to do here first is I'd like to introduce the overall concept of clustering. So essentially our overall goals of what we're trying to do with a cluster analysis. But in addition, I'd also like to model and showcase how cluster analysis specifically fits into the full data science pipeline. So we're going to be thinking about other decisions that we might want to consider when it comes to performing this cluster analysis. So for starters, when we conduct any type of data science analysis, there's usually some sort of goal in mind that we have for the data set that we have in our hands or that we'd like to collect. And usually even before stipulating the goal, we should have some sort of motivation for why we want to pursue that goal in the first place. So this is kind of like a potential motivation for why somebody might want to cluster the data set that we're going to be exploring here in this unit. So for instance, like I mentioned, I used to work in online advertising. And, when I was working for that startup, a friend of mine, she was, wanting to basically start up her own yoga studio. She had just moved to the area and she was wanting to, advertise, I guess you could say. She didn't have enough people, coming to her yoga studio. So she comes to me, she's like, Tori, I'm not getting a lot of people showing up to the yoga studio. How, you work in advertising. What's the best way for me to really pull in the right kind of people who would be most likely, to actually want to come to my new yoga studio? So, when it comes to the world of advertising, there's generally three main categories, I guess you could say, of strategies that advertisers like to use. So, one strategy that mega corporations like Coca-Cola, Pepsi use is what might be considered or called blanket advertising. So this is where companies who have a lot of money, can place a billboard in the middle of Times Square. They can, put a commercial, prime time during the Super Bowl, for instance, trying to motivate you to buy a Pepsi. Now, the thing here is like the amount of return on investment that you get by placing that very expensive ad in these very expensive locations, is really potentially not all that much. So for instance, maybe only 2% of people who have been exposed to your ad may actually be so motivated to, go out and buy a Pepsi. But the thing here is, given how many people were actually exposed to that ad, and given that you had the money to actually pay for that, ad spot, it actually ends up being a very lucrative investment for you nonetheless, even though a very small percentage of people are actually, were motivated by the ad in the first place. Now, my friend opening up the yoga studio does not have such kind of money. So that option was off the table. Now, another strategy that some companies use is what we call micro-targeting. And this is where they would elicit the services of companies like the one I used to work for, where we basically collect, I would say, I think we had for a very large database of internet users, we had about 50 to 70% of traffic, or 70%, if you will, of the websites that they had visited. We had records on all of those websites that they had visited. Very creepy. But what it allows for us as the data scientists to do is essentially to develop sophisticated micro-targeting algorithms, which have very high prediction rates, if you will, for you basically predicting whether or not a given individual person would be motivated to purchase that particular product based on the decision or based on the ad that they were presented. But there's a lot of cost constraints that go into micro-targeting as well. So for instance, it costs a lot of money for online advertising agencies to, collect these huge databases of, everybody's browsing history. So therefore, it also costs a lot of money for, companies to elicit these micro-targeting services. So unfortunately, micro-targeting was also off the table for my friend as well. So we went from a very broad marketing strategy to a very micro-target or very individualistic marketing strategy. And so what actually would end up being most cost effective for my friend or other people who don't have that kind of money is sort of a middle ground solution. So we call this market segmentation. And so this is the process where we basically take a potential market of customers and we divide them into what we call market segments, or using more formal language, which relates to what we're doing here, clusters based on different attributes about those particular people. And then basically these segments or clusters are in theory composed of consumers who will respond similarly to the marketing strategies, and perhaps also those who share similar interests, needs, and locations. So the general strategy would be to first create these market segments or clusters using a cheap data set, based on, certainly not the entire browsing history, but based on key information, for instance, that we know about the people. We'll look at a data set such as that. And then we explore what makes the people in each of those clusters similar. What do they all have in common? What do they all tend to like? What do they all tend to not like? And then we pick the market segment or the cluster that we think is comprised of people that would be the most interested in attending that yoga studio. And then we basically just show customers in just that market segment, maybe online ads, maybe some sort of a mailing service, if you will, for the yoga studio. And the thing here is, if you've ever used social media, which I'm assuming all of us have, everybody belongs to probably a lot of different market segments. So for instance, if anyone's still using Facebook, I know for a fact that Facebook actually allows for you to see what market segments they think that you belong to. Now, this is kind of proof that we don't actually, as data scientists, we don't get it right all of the time. So for whatever reason, this is my Facebook profile picture. They deemed me as belonging to the baby boomer market segment. I'm not sure why, but if anybody doesn't know what baby boomer means, it's basically someone who's the same age as my parents. So a little bit offensive, but I'll get over it. So basically everyone probably belongs to some sort of market segment. And these companies will use that information to, basically target specific ads to you. So that's one motivation for why we might want to collect a cheap data set and cluster it. And so the cheap data set that we're going to end up using to build our market segments is this data set that you can see in the CSV file that I've posted for Unit 1. And it's basically a set of 980 people who have been to a variety of different types of travel destinations. So like art galleries, dance clubs, and they each have given their own respective rating for each of those types of travel destinations. And the person who created this data set essentially gave their average rating for each of these different types of travel destinations. Okay, so basically the bullet point is we're going to take this data set, which has 10 columns and 980 rows, and we will cluster it to best help my friend figure out who are the best people to advertise her yoga studio to. Okay. I'm a little bit out of breath. Any questions before we move on? Okay. Now, before we dig in to actually performing a cluster analysis, like we mentioned, we want to think about how each of the parts of the data science pipeline that precede the use of a cluster analysis might actually influence decisions that we make later on in the data science pipeline. So what we want to remember, again, is that cluster analysis is a type of descriptive analytics technique. We're using it to basically describe the data set. That's our ultimate goal. So before using a more sophisticated descriptive analytics technique, it's always a good idea to, perform more basic descriptive analytics techniques. So basically, summarizing each of the individual variables, summarizing the relationship between each pair of variables. So for instance, we can take a look at the, histogram for each of the travel destination types. So, average rating for art galleries, dance clubs, so on and so forth. So far, nothing looks too suspicious yet, except for perhaps this histogram here. So let's think about this here. So let's just say, for instance, we decided, we only wanted to cluster just this variable. So just throw out the remaining variables and just cluster this into like-minded groups. So the question is, if we did that, and then let's just say we applied k-means clustering, do we think perhaps that the clusters that this algorithm would have identified, do we think that any potential clusters that we identify, do we think that they're actually meaningful? So that's my question to you. So try to think about, what types of groups might a clustering algorithm split this variable up into? And then would those groups be meaningful? And if you have an opinion, start typing up your answer in the chat because I want to know why. Right, so I'm seeing a lot of no's. So why do we think that? So let's first think about like what types of clustering results a sensible clustering algorithm might give us. So for instance, I'm seeing some sizable gaps that exist here, here, and here in the data set. So even just kind of like thinking about what we see with our eyes, it might, in all likelihood, if we applied a clustering algorithm to just this single variable, we might actually end up getting 5 clusters. So 1, 2, 3, 4, 5. So if an algorithm was to cluster this into 5 distinct clusters based on these gaps here, why would we think that perhaps these would not be the most meaningful clusters? They are already very obvious. Well, yeah. So yeah, clustering just a single variable tends to be, we technically don't need an algorithm to do it because we can see the gaps with our eyes. Um, something about the scale, the responses are so similar. Yeah, because basically we can see with these other histograms, there's a lot of distinct boxes, whereas which basically reflects that there's um, the range of values that we're looking at are continuous, as opposed to this histogram, which is showing us only 5 discrete values. Now, I'm a little bit suspicious as to why there's only 5 discrete values. Why are there only 5 discrete values? That might be a question that I have. And, I might also ask, are there only 5 discrete values due to some, data processing step taken? And so the question is, if we were to basically just split this data set up into 5 groups, um, it begs the question like, well, are these separations that we're seeing here, are they actually meaningful, or are they simply just due to some sort of rounding process that was taken? So if it was simply just due to some rounding process, I would be skeptical that there's actually anything meaningfully distinct about these observations. So this kind of just showcases how even, exploring a data set, even before we get into the more sophisticated algorithms, can provide useful insight. So for instance, you may decide that you want to get rid of this variable because it could perhaps make it seem like your data set has more meaningful separations when it actually doesn't. So something to think about. Um, da, 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 da. Yeah. So I'm seeing something about a rounding gap. Yeah, so I think it could be, yeah, because of a rounding gap. Yeah, that's what we discussed here. Yeah. So basically, we want to ask the question is, creating distinct groupings based on a simple rounding gap meaningful to Corey's friend? Probably not. Okay. So moving on, we'd also want to look at, as best as we could, any pairs of relationships that exist in the data set. So we might look at every pair of scatter plots that we could create with these 10 variables. And for the most part, I'm not seeing a whole lot of separation that exists between sets of observations here. With maybe we're seeing like a little bit of a separation here. Maybe there's something going on here. And again, we're also seeing that same perhaps rounding gap issue showing up in that same variable here. So if we weren't careful, it's possible that a clustering algorithm might simply just return these 5 sets of observations and claim that it's a meaningful cluster, when it may actually not be. So this kind of showcases it's really important to look at your data ahead of time. But the thing here is just because we're not seeing a big or like a strong clustering relationship in our 2-dimensional plots doesn't necessarily imply that a clustering relationship doesn't exist in higher dimensions. So for instance, here we can see these, like if we take a look at these 2 variables here, so x and y, we do see by looking at the scatter plot, there is a clustering relationship. There's a very unique distinction between the orange points and the blue points. However, if we were to simply just look at, visualize the X variable, to look at a histogram, we wouldn't end up seeing that clustering relationship. So really the only true way to know visually if a clustering relationship exists in 10 dimensions or 10 variables is to look at a 10-dimensional scatter plot, which is something that we cannot do. So therefore, we need to employ the use of clustering algorithms to help us truly detect whether there exists a clustering relationship or not. So basically, that's going to be our first step in our overarching research goal. So first, we ask ourselves, do there exist distinct clusters or market segments in this data set? So basically, is returning a distinct set of clusters, is it going to be meaningful? Or are we simply just taking a blob of points and cutting it up? We don't want to do that. And if so, if there do exist distinct sets of points in the data set, how many? How many clusters are there? Now, this is the most important part for an actual real-life analysis, is basically once we've identified the inherent number of clusters that exist in a data set, we then want to figure out what characterizes each of those clusters. So for instance, do people in one cluster, do they tend to prefer like juice bars and, art galleries more than the people in the other cluster? Maybe if that's the case, maybe that would be a good group of people to, advertise the yoga studio to. So basically we need to figure out what characterizes those clusters and then think about how we can use those insights, for our overarching research goal, our motivation, if you will. So questions on that? Okay. So in comes the goal, or a more advanced descriptive analytic techniques of using a clustering algorithm. So a clustering algorithm can basically answer all of those questions for us. So I'm going to give you a very vague general statement of a clustering algorithm because, again, there's a wide variety of different algorithms that exist. But generally speaking, the goal of a clustering algorithm is to think about how to best group a set of objects into clusters such that the similarity of the objects in the same cluster is maximized, while the similarity of the objects in different clusters is minimized. Okay? And again, like we've seen in the first unit, this notion of similarity is a bit vague. And the reason why we keep it vague is because based on different notions of similarity, we may actually get better or worse performance for given data sets when we apply that given clustering algorithm to it. So a more formal definition, I see a question here, I'll answer that in a second. Actually, I'll answer it now. The question is, how does this connect to finding out which market segments to advertise to? So basically, once we find a group of people, we're going to learn about what do they like, what type of trips do they most enjoy. And for instance, we'll kind of giving the ending away here, but for instance, we might think that's like, well, okay, maybe people who like art galleries or juice bars, that's gonna be the key thing here, are more likely to want to come to a yoga studio as opposed to maybe people who like religious institutions. So we're going to look at what characterizes the people in each of those groups, and then use that to make a best decision about what they also might like. So there's a little bit of qualitative analysis in the end that you want to think about. Okay, so I want to give a formal definition of what we call a cluster and a clustering. And again, I'm going to be giving you some vague definitions here as well. So for a given set of objects, we call a cluster a subset of these objects, basically. And a clustering is simply just a set of clusters that we have created. So we want to think about how this definition that we've just given might be vague. So let's think about this cluster or this set of subsets here that we've created from a set, total set of objects, x1 to x4. So the first question is, do we think this first set of subsets is that a clustering? Hold on one second. So is this a clustering based on this definition that I gave you? Okay. All right, so it looks like we are in unanimous agreement that this, in fact, is a clustering, right? This would symbolize, oh my goodness, I'm so frustrated with my computer right now. Give me one second. So this would, Jesus Christ. I would put these two observations together in a cluster, and that would put these two observations together in a cluster. And so, yeah, so we call this specifically a partition-based clustering, in which basically every observation is assigned to one and only one cluster. So when we talk about k-means in this unit, we'll see that k-means is what we call a partition-based clustering. So every observation gets assigned to one and only one cluster. Now let's think about this second set of subsets that we've created here. So based on the definition that I gave you, the question is, does this count as a clustering? Okay. So I'm seeing mostly no, but actually simply just based on this very vague definition that I've given you here, the answer is actually yes, this does actually fit the definition that we were given. So for instance, we can see here that X1 was actually assigned to two clusters. So there's nothing in this definition stipulating that an observation has to belong to one and only one cluster. Okay, so this is kind of showcasing how this definition is a little vague. So not all observations have to belong to one and only one cluster. So what we've actually shown here is what we call an overlapping clustering, in which it's possible for an observation to belong to more than one cluster. Now let's look at the final set of subsets that we've created here. So one final question is, based on this definition that we've given here, is this a clustering? Okay. Ah, cool. Okay, so I'm seeing I've split the class 50-50. So again, simply just based on this very, this definition, which is very loose in terms of constraints, this set of subsets here is also, in fact, a clustering as well. So take note that X1, one of our observations in the set, does not actually belong to a cluster. But again, based on that definition, that's okay. We're not requiring every observation to belong to a given cluster. And so this is actually going to be useful, for instance, in a clustering algorithm, which we call dbScan, which is both an algorithm that is designed to cluster observations that are not considered noise. And it also identifies that if an observation is a noise point. So if it identifies an observation as a noise point, it actually does not cluster it at all. It simply just throws it out. It says, don't cluster it. So this is one such type. It's one type of clustering algorithm. that does not cluster all observations. Okay. So we're setting up a very vague or very broad definition of a clustering, and it's simply just a set of subsets or clusters of a given set of observations. Okay. Questions on that? Dokie. All right. So again, clustering, or the general goal of clustering, we've stated it in a very vague way because the way that we define similar of many other questions that we might ask is, yeah, it's going to be different based on different clustering algorithms that we might use. And furthermore, our notion of object similarity is going to be more or less effective for different types of data when it comes to actually identifying meaningfully separated clusters of observations. So let's so I'm seeing a question here. It says, can we have an empty subset? So yes, we can. So for instance, k-means, which we're going to talk about usually. So, one of the things about k-means is that we have to specify how many clusters that we would like ahead of time to cluster observations into. But sometimes, very occasionally, it's possible that your k-means clustering algorithm will end in which you actually have an empty cluster, or there's no observations assigned to it. So that is also a clustering as well. So it's a good question. So to kind of further elucidate this point, how different notions of object similarity can help us dictate different types of clustering algorithms that exist. Let's take a look at these three different types of data. So here we have a two-dimensional tabular data set that we see here visualized in the scatter plot. And then here we have a image-based data set. And we can use so if you're ever looking at an image data set, we do have ways of basically translating a image into a tabular data set. So for instance, we might zoom in on a person's face and then basically represent the numerical pixel value in each pixel of the face, and then translate that into an array. And then basically that row represents a person's face. So for instance, this data set could be transcribed into a series of arrays or pixelated arrays of each, people's faces, if you will. So on and so forth. Okay. And so the final data set that we might want to explore is a graph-based data set or a network. So for instance, this could be like a social network in which, if each of the nodes represent like a person, and if you see an edge between the nodes, that represents some sort of meaningful connection between, two sets of people. So we'd also want to think about, for each of these given types of data that we've just described here, what would be a good way to define similarity between the objects such that our definition of a clustering is able to identify meaningful clusters? So you want to think about, for each of these data sets, what is a meaningful cluster? We can kind of get a sense with our eyes here, but really try to think about what's a good way to measure object similarity such that our vague definition of a clustering would actually be able to identify meaningful clusters that we can see with our eyes. So I'm going to ask you guys that in a breakout session. So I'll open up the breakout rooms and discuss that. So basically give your best guess about how to define similarity for each of these three data sets. And then we'll meet back and discuss. Okay, so I'll start just randomly assigning people to breakout rooms. You can always change if you'd like. And try to meet in a breakout room with about 4 people. Okay. So everyone should have been assigned to a breakout room. So we'll meet back and discuss. Okay. So give people a few seconds to come back. So yeah, hopefully you were able to generate some interesting answers for how you would go about answering this question for each of the three data sets. So let's start with well, maybe you've seen this data set before. It's like literally the most popular clustering data set that exists. This is the iris data set. It's comprised of like the height and weight of petals of different types of iris flowers. So yeah, so this is a two-dimensional data set comprised of two numerical variables. So based on what we see here, what would be a good way of defining similarity between two objects such that our definition of a clustering would be able to effectively identify the three clusters that we can see here with our eyes? Oh, wait, did you guys hear that? Was I muted? Just checking. Do people hear what I'm saying? Okay. Okay, good. So what's a good distance metric or a way to define similarity between two objects here in this example? Yeah, so that'd be a good place to start. So similarity means, yeah, small Euclidean distance. So yeah, so basically we can see that, all these observations here in this cluster that we can see with our eyes, yeah, all have a relatively small Euclidean distance with each other. So therefore, if we put observations that are relatively similar to each other, or if we define similarity in this way, then yeah, we basically see that under that definition of a clustering or an ideal clustering, and under this definition of similarity, that yeah, basically all these observations are similar to each other. More or less all these observations are similar to each other, and more or less all these observations are similar to each other. Okay, good job. And then what about this? How would we define the similarity between, two pixelated face arrays um, in this data set, such that we can essentially find similar faces, basically more or less corresponding to the same person like we see here? Hair color intensity, that's interesting. Yes, I mean, so maybe if you only have one person with gray hair, then I guess that could help pick that out. But what if they all had the same hair color? Yeah, skin tone. I mean, so these are all kind of focusing on very specific things. But the question is, how does a algorithm know what's the skin, what's the hair, what's, nose? So these are all specific questions, but we would need to be really, we'd essentially would want to automate this process. We wouldn't want to like actually, you know, go into these images ourselves and like, pick out the noses, pick out the hair. Ideally we'd like an algorithm that didn't require any manual input from us. So basically the question is how can we evaluate whether simply just two arrays are similar to each other? And let's just say they didn't even have to be faces. Like what if they were like cars or something? Yeah, so basically, I mean, theoretically, technically, you could also use I mean, these are simply just two, I don't know, like 64 dimensional arrays that we're trying to measure the similarity between them. So if you're ever trying to measure the similarity between two rows in a data set, the Euclidean distance, technically always works. Another similarity metric that people use, particularly when looking at the similarity between images, so two pixelated array representations of an image, for instance, is the cosine similarity. But yeah, basically, if we see that there's a lot of similar pixelated values, like so there's similar pixelated values here, here, and here, then yeah, basically that means that those images would be very similar to each other. And so ideally, if we've kind of positioned the faces just right, if you will, that would cause, the same person to basically show up in the same cluster. Okay. Any questions on that? Okay. And then finally, so we can see with our eyes that there do exist 5 meaningful clusters or similar groups of people in this network here. Now, this is a slightly trickier question. So how might we define whether two nodes in this network are similar such that sets of observations, let's just say in this group of people here, are considered all similar to each other? But sets of observations here in this cluster are considered generally dissimilar to each other. So these people are dissimilar from these people. So how might we define similar in this case? So something about centroids if a node is connected to the, well, so let's assume that we don't have that color. The color is more for us to kind of, this is how we've clustered the data set. So assume that we don't have that color attribute. Any ideas? Well, so let's try this. Let's see if this makes sense. So let's define two nodes as being similar. No, go away. The similarity between two nodes is equal to the number of neighbor nodes that they have in common. Okay, so for instance, we can see that this observation here is pretty similar to, actually, so hold on. So this observation here is very similar to, let's just say, this observation, because they both share a lot of common connected observations. So that tells us that they're very similar. I'm not sure what this word means. But on the other hand, even though we do see that these two observations here are connected, they do not share any connected neighbors. So basically, under our notion of similarity, these two observations would actually not be considered similar. So with this notion of similarity, basically, we can create these groupings of people based on the common networks or the people that you have in common. And that kind of makes sense, like if you're in a friend group, chances are, you're probably also friends with, like, so if you're talking about you and one of your friends, if you guys are together in a friend group, you probably also share a lot of common friends as well. Okay? Any questions on that? Okay. Second. Okay, so we're going to focus for the first part of the class on focusing simply just tabular data. So for instance, if the question is, how would you know if two nodes are in common? So the edges in the graph are given to you ahead of time. So you would know, that might be something where like people tell you that they're friends, for instance. That would be something that they stated in the data set. So focusing on, let's just say, an ideal scenario with a, let's just say, two-dimensional data set. So for instance, if we were only, wanting to cluster just two of those trip types, so like preference for juice bars and preference for art galleries, then this would actually be a really easy task, right? So we could simply just create a scatter plot, and then we basically be able to see with our eyes the answer to all of our questions. So we can see that, number one, this is in fact a clusterable data set, so there do exist meaningful groupings that are separated from each other. Number two, we'd be able to see that there are 4 natural distinct groups or clusters that exist in the data set. And we can also see which observations belongs to each one of those 4 clusters. On the other hand, it is possible that we have this data set that looks something like this, where it's basically just a blob of points. There's no meaningful separation that exists in the points. And so we call this a unclusterable data set. So it really wouldn't make a whole lot of sense to perform a clustering algorithm on it, because essentially you would be implying that, let's just say you clustered it into 2 clusters, you'd essentially be implying to my friend that there is something meaningfully distinct about these 2 sets of observations, when we can see with our eyes that there isn't. Now, the problem is we're dealing with a 10-dimensional data set, so we're not able to see in 10 dimensions, the answers to these questions. So therefore, we need to use a clustering algorithm to answer all these questions for us. Okay. So one of the most common clustering algorithms or clustering optimization problems, there's a distinction that we use in cluster analysis is known as k-means. Now, before introducing the k-means clustering algorithm, I'm going to first introduce the k-means clustering optimization problem. So the input for both the k-means clustering optimization problem and the algorithm is the following set of things. So first, you need a set of numerical variables. So that is a key important element here. And basically, your data set should be tabular. It should be comprised of m observations with n attributes, all numerical. And then furthermore, this is one of the, this is something you need to think about ahead of time, is what number of clusters would you like to cluster your data set into? Okay. Now I'm going to give you another vague statement here as well. So the general goal of the k-means clustering optimization problem is, out of all possible clusterings of a set of observations that you could create with k clusters specifically, our goal is to find the optimal clustering of these k clusters that specifically minimizes the sum of the distance between each observation and the mean of the cluster that it was assigned to. And so we also call this mean the centroid of the cluster. Okay. Basically, here we have all of our observations. This is the mean or the centroid of the cluster that they were assigned to. Okay. And we simply take each of these distances, we add them up, and that is what we are trying to minimize. Okay. Now, simply just in this statement here that I've stipulated, how is this definition vague? Exactly. So how do we define distance? Now, I'll say this here first. When talking about, I'll say this, in the k-means optimization problem in particular, the distance metric can be whatever you want. Okay. Now, when we introduce the k-means clustering algorithm, or what's more formally known as Lloyd's algorithm, we actually need to get more specific about what distance metric that we're using. So we're actually going to use the squared Euclidean distance as our distance metric. Between every observation and the centroid. And we'll talk about why in a second. But basically, in every optimization problem, there's some function that we are trying to minimize. We call that the objective function. So in particular, the objective function that we're trying to minimize in k-means, we call that the inertia. So it's the sum of the distances of each observation to their assigned cluster centroid. Okay? Questions on that? All right. And so, given that this is an optimization problem, we are trying to basically find the minimum inertia out of all possible clusterings with k clusters that we can make. So given that this is an optimization problem, the best case scenario is that we are able to find this clustering that is a global minimum to this problem. So in other words, it's the absolute lowest possible inertia that you could basically get. Now, unfortunately, the k-means clustering optimization problem, the act of finding the global minimum to this problem belongs to a class of optimization problems called NP-hard. Okay. Now, we're not going to get too much into computational complexity theory here in this class, but practically speaking, what it means is that the task of designing an algorithm that will find this global minimum inertia quickly, that's the key thing, especially as the number of observations or attributes increases, is highly unlikely. So bullet point is, we certainly have not found an algorithm yet that will quickly find this global minimum solution for you. And given that it belongs to this class of NP hard problems, it's highly unlikely that we ever will. So we need to do the next best thing. We use instead what we call heuristic algorithms. So instead, we use what we're going to call Lloyd's algorithm, which is a heuristic algorithm. Second. That in a relatively fast amount of times, quick amount of time, will find not unfortunately, the global minimum to this, but it will quickly find a local minimum to this objective function here, or to the inertia. And by that, we mean basically that, if you keep engaging in the same series of steps, eventually you will get to this point where here on your y-axis is the inertia. Eventually you'll get to this point in which any other step or any other movement any other iteration of the algorithm will lead to a worse outcome, or basically a higher inertia. But that doesn't necessarily mean that the solution that the algorithm arrives at will be the global minimum, but it will be a local minimum. Now, usually the local minimum tends to provide relatively good enough solutions, so we tend to be okay with the fact that it's not guaranteed to give us this global minimum solution. Okay. Any questions on that? Okay. All right, so what is this heuristic algorithm? So we call, more formally, this algorithm is known as Lloyd's algorithm, but it's also colloquially known as the k-means clustering algorithm. And so the input for the heuristic algorithm is exactly the same as the optimization problem. So we need the numerical data set, M objects and attributes, and you also need to pre-specify the number of clusters that you're looking for. Okay, so basically the algorithm has 4 basic steps. So the first step is we randomly initialize the centroids, or basically randomly initialize our k-means. And so basically the way that one way that you could go about doing this is basically take a look at like a general window that's roughly around the points, the range of values in your data set, and then simply just randomly select a x-axis value, randomly select a y-axis value, and that could be your first centroid. So this will be my initial centroid 1, and this will be my initial centroid 2. Okay, and do take note, there is an inherent random element to this initialization step. Okay, and the next step is the cluster assignment step. So basically in step 2, you're going to assign each object or observation in the data set to its closest centroid. Now I'm going to be specific about how I'm defining closest in the context of the heuristic algorithm in particular, and I'll say why in a bit. But in this case, when we say closest, we mean the smallest key thing here, squared Euclidean distance between the observation and centroid. Okay. And the reason why we're specifying this particular distance metric is because the algorithm is only guaranteed to converge to a local minimum if we are using the squared Euclidean distance specifically. Okay, so this is a key thing to note here. Okay. All right. I'm spelling that wrong. Okay. This is not going to work with my pen, but I'll try. Okay, so basically we can see that each of these observations here are closest to this centroid. So all these observations get assigned to cluster 2. And then we can see that each of these observations here are assigned to, or closest to this centroid, so they get assigned to cluster 1. Okay. And so the next step is the centroid update step. So basically, we are going to find the mean of each of the current clusters that we've created in step 2. And then basically these means are now the new centroids. Okay. So going back here, we can see that the mean of all the x-axis values of these observations is something like here, and the mean of all these y-axis observations of the points here is something like here. So that's not a good color to use. So basically, the new centroid for this cluster would be something like right here. So this is new centroid 2. And similarly, the average of all these points in this cluster would be something, some observation here. So this would be new centroid 1. Okay. And so final step is evaluating our stopping criterion. So if the old centroids and the new centroids are the same, then we basically stop the algorithm and we have our final local minimum clustering. If not, we simply go back to step 2 and begin again. Okay. All right, questions on that? All right. So, oh goodness. So basically we move on to the next iteration. And so my old centroids are going to be here and here. Old centroid 2. And this is my old centroid 1. Oh, I'm so yeah, hold on one second. All right, no, okay, sorry. Technically, my pen's a little funky, so I kind of got a little lost here. So technically, some of these observations are actually closer to this centroid here. So maybe some of them should have been assigned here. So let me just modify that here a little bit. Okay, so actually, this cluster would still be split. So this would be something more like this, and would be like this. And so that would actually place the new centroid a little bit further to the right in both of these clusters here. So that new centroid would be somewhere like this, and this new centroid be something like this. Okay, so that means this old centroid would be a little bit further, yeah, to the right. This old centroid would be a little bit further to the right. Okay, and so now we basically conduct the same step 2 again. So we assign each observation to their closest centroid. So now basically each of these observations are closest to this centroid. Each of these observations are closest to this centroid. And then step 3, the centroid update step, we would find the average of each of the points in each of the clusters. So that would create this new centroid 2 and this new centroid 1. Okay. And because we can see that the old and the new centroids are not exactly the same, that means we move on to the next iteration. Okay. And so Here's my old centroids. So the old centroids become the new centroids. Okay. And again, I'm going to assign each of my observations to their closest centroid. Get this and this. That's step 2. And then in the centroid update step, I'm going to take the average of each point in each cluster. So now my new centroid is here, and my new centroid is here. Okay. And so now I can see that my new centroids are exactly the same as my old centroids. So therefore, the algorithm stops, and this is our final cluster. All right, so I'm seeing a question, is the inertia of new clusters always larger than old clusters? Yeah, so basically, if your centroids are not in the same location, then that means that your new inertia will always be smaller than your old inertia, basically. Yeah. Okay. All right, any questions on that? Okay. So I've got 10 minutes left, so I'm trying to be judicious with my time here. I did not get to all the things that I wanted to do. I'm going to skip over this here really. I'm going to skip over this because I do have a homework assignment more or less prepared, so I want to get to some of the key things here first. Okay, so we'll talk about the pros and cons of k-means clustering on Tuesday. But I do want to talk about basically the ideal types of data sets that the k-means clustering algorithm is designed to work best for. So again, like we mentioned, every clustering algorithm is going to work better or worse based on the type of data set. So now, what that means is that basically every data set has a set of ideal properties for a given clustering algorithm. But the key thing that you want to remember is that even if a data set does not necessarily meet all of these ideal properties, does not necessarily mean that the algorithm won't be able to identify the clusters that exist, but basically that the data set will be more ideal for that particular algorithm. So it's more likely for the algorithm to identify the actual underlying clusters that exist in the data set. So here are the ideal properties of a data set and a clustering and that the k-means clustering algorithm is designed to work best for. So number 1, each cluster that inherently exists in the data set should have roughly the same number of observations in it. That's 1. 2, each of the shapes of the clusters should be roughly spherical. Number 3, each of the inherent clusters that exist in the data set have roughly the same sparsity. So this is not meeting that condition. 4, there should be relatively good separation between the clusters. So for instance, if you have a set of clusters that looks something like this, that is not a set of well-separated clusters. Okay. 5, when you're using the k-means clustering algorithm, you know the right number of clusters to ask for. So basically, if there inherently exist 3 clusters in the data set, but you ask k-means for 4 clusters, then you're not going to get a very insightful result. Number 6, each of your attributes should be numerical. So when you're dealing with like categorical variables, k-means does not tend to work as well. So we'll introduce another algorithm that works for categorical variables. And finally, your data set ideally should not have a lot of noise and outliers. Okay. So someone is asking the question, right? And this is always a very key, next question to ask, right? How will we know the right number of clusters to ask for in a real world data set that we can't actually see with our eyes? So that's a good question, and we're going to answer that hopefully today. I am going very slowly. In the next slide, basically. So just to test your understanding, which of the following two data sets do we think would be better or more well suited for k-means? I'm going to put a poll. Hold on. Data set 1 or data set 2? That is the question. And if you have an opinion, if you think one of these data sets does not meet all the ideal assumptions, start writing up in the chat what are some problems with the data set that you've identified. Okay. All right, I think I've stipulated a very easy question here. Good that we're all on the same page. Okay, yeah, so data set 2, this is more ideal. So what's the problem, or what are some problems with data set 1? So someone's saying not the same sparsity. I'm a little unsure about that because, I mean, I would say more or less these observations all look, they all roughly have the same amount of spacing, if you will, between each other within the cluster. So I think we're good on the sparsity. But yeah, I'm seeing number 1, they're not all clusters are spherical. So that's one key issue. Yeah, so not all clusters are well separated. That's another issue. Yeah, and then the final one is not all clusters are roughly of the same size. Someone's saying outliers. I don't really see any strong outliers here, so I think we should be good to go on the outliers. But yeah, basically these 3 things may make it more challenging for k-means clustering, or for k-means to identify the actual inherent clusters that exist in this data set that we can see with our eyes. Okay? Questions on that? Okay, so someone asked a very valid question. You know, let's just say this is not a 2-dimensional data set. It's, you know, not a data set that we can see with our eyes. How do we know, or how might we guess what is that inherent number of clusters that actually exist in the data set? So one approach that we take to not just identifying if a data set, or not just identifying how many clusters exist in a data set, but also identifying if a data set is clusterable at all, or basically if there's any separations, is what we call the k-means elbow plot method. So here's how it works. So what we do is we pick a range of cluster number values going from 1 to like 20, and you want to think carefully about what is this upper bound, you know, because this can affect like the insights that you see. So let's just go with something high like 20. Now for each of those cluster numbers, what you're going to do is you're going to cluster the data set using k-means into that number of clusters. So maybe what I might do is, you know, first I'm going to cluster the data into just one cluster. And I'm going to do it 3 times, let's just say. And then what I'll do is I'll cluster the data into 2 clusters. And then I'll do that 3 times. Then I'll cluster the data into 3 clusters. And I'll do that 3 times, so on and so forth. Okay? So basically for each k cluster number, I'm going to calculate the inertia of each of those clusterings. And I'm going to calculate the average inertia. So the average inertia of these clusterings, the average inertia of these clusterings, and the average number of these clusterings, so on and so forth. And so what I'll do is plot the cluster number on the x-axis, the average inertia of those corresponding clusterings on the y-axis. And I'm going to interpret what I see based on whether or not a elbow exists in the data set or not. Okay? So basically, here's how I go about interpreting this k-means elbow plot. So basically, we want to be looking for a very strong, or we want to look for an elbow, basically, in the plot. So we see a little bit of an elbow here. It's like a little bit of a dip, if you will. A complete lack of an elbow would look something like that. So we don't see that. So basically, if we don't observe a dramatic elbow, so something like this, that either means one of 2 things. So it could mean that the data set is not clusterable at all, right? So basically, it's just like blob of points. There's nothing meaningfully separated about those points, so on and so forth. On the other hand, though, it could also mean that there is a clustering structure in the data set, but k-means is not a suitable algorithm for identifying that clustering, right? So basically, if we had tried to get k-means clustering to identify these two clusters, it's not going to work. It does not meet a lot of the specifications. So it could be one of two things if you don't see an elbow plot. I'll wrap up here. On the other hand, if you do see a dramatic elbow, then number one, it does suggest there is a clustering structure in the data set. And furthermore, k-means clustering, or the k-means clustering algorithm, is suggesting that there are about that number of inherent clusters in the data at the point in which you start to see the plot leveling off. So for instance, I'm looking at this elbow plot here. I see the most amount of leveling off here. So what that might suggest that there, or that it means at the very least, is detecting 3 inherent clusters in the data. Okay. All right. So unfortunately, I realize that some people did not request this in the getting to know you survey. I may need to add an additional 5 minutes of content, basically at the end of this class, like just basically showcasing how you will actually code this in Python. So I'm just going to add 5 additional minutes of content after I sign off here, basically just showcasing how do you actually do this in k-means, or basically in Python. So it shouldn't take too long, but bullet point is you will need that information in order to basically complete the homework assignment that I'll be submitting. So it shouldn't take too long. I don't plan to add a whole lot of additional content, at the end of class, but we are running a little bit behind in this particular class. So I'll send out an email when that additional video content is ready. But yeah, I think that's basically it. Yeah, okay, so I think we'll wrap there. If you have any questions, feel free to stick around after class. I do see a question here. So I'll stop recording.